Thank you. Thank you so much. Thank you, Sairaj, for a very kind introduction. And so, yeah, we actually haven't synchronized the presentation, but we've been working together for several years now, both on hardware in the loop simulation for power electronics and power systems, as well as kind of like a very interesting course on grid forming converters. So my first part of the talk will be less interesting. I'll talk a little bit about kind of like Typhoon and hardware in the loop simulation, and why we do what we do, and how hopefully this can be useful for not just UNIFI, but kind of the whole process of digitalizing, decarbonizing, and decentralizing grid. And then Professor Humberto will talk a little bit more in terms of the course that we have implemented and kind of how we approached it from a little bit different perspective of test-driven design, which is something that people often do for software projects and software development in general, but maybe not so much for power electronics. So I always like to start with a little bit of history and kind of like look literally how we got to where we are today and how our grid looks like. I'll also mention differential analyzer. For some of you guys that might not be familiar, one of the very first applications of differential analyzer in 1920s was actually as the grid simulator. We'll actually then we'll switch a little bit gears and kind of try to understand what this D3 is bringing to the whole story and why things are changing, and kind of like how and why we focused really on model-based control development, testing, and validation, and maybe demystify a little bit our idea of how these digital twins of power converters, which we call Hill-compatible models, can actually be useful. But before we start, maybe some of you guys are not familiar with Typhoon. So just a really brief overview. So we are, I wouldn't call us a startup company anymore. We started a little bit more than 10 years ago, spun off from MIT and ABB. Our main focus from day one was this ultra high fidelity real-time simulation for power electronics. And our initial huge success was that we managed to simulate power converters with 1 microseconds in real time. I mean, since then, it's more than 10 years now, we have more than 500 power electronics, drives, e-mobility, microgrid, and power system customers. And we're actually crossing this 100-employee barrier with a little bit more, actually 6 offices and a few more in the making. So this is our footprint, not just our offices distributed, but also value-added reseller. And we really like to be as close to the customer as it gets. So we're really excited and eager to contribute to UNIFI and help forward the cause of broader implementation of grid forming inverters for our future grid. So in terms of when we look back, so I really like always to kind of spend a little bit of time thinking about how we got where we got there. And we all know in 1880s, we built Thomas Edison actually built the first DC. I mean, you could call it a microgrid, a small local distribution system. But then very quickly, actually, we started going kind of different direction with the AC distribution, and of course, famous Westinghouse, Tesla, Niagara Falls hydroelectric development, which then basically we built the transmission line to connect New York City with this generator. And what actually ensued after that is that people actually started building kind of like somewhat decentralized grid where they would have a synchronous generator source, somewhat well coupled with the loads, and then very quickly they realized, well, okay, if we start networking these, we might actually be better off. 1922, we actually built we got the first 245 kV line was commissioned, and then kind of like 1935 was the Federal Power Act that basically brought the kind of like the ability to have the wholesale transmission and sale of electric power, and so on. But very early on, when people started paralleling not converters, but when they start paralleling the sources, synchronous generators at the time, they started actually noticing the instabilities on the grid. And these first instabilities, they really didn't understand that well. Turns out at the time there was a professor at MIT. His name was Vannevar Bush, also a pretty famous guy for many things, among others that he was Claude Shannon's master's thesis advisor and started the NSF Foundation afterwards and was the first science advisor to FDR. He basically was one of the first guys to build this simulation machine. I like to they called it differential analyzer, and fundamentally what it did, it was real-time simulator of dynamic systems, where you were actually kind of like able to simulate different sets of differential equations and change the parameters by changing some of the kind of mechanical couplings and inertia and things like that. And this is kind of considered the beginning of scientific computing in my mind. This analog twin, the way I call it, differential analyzer, was also used later by Edith Clark. And she actually cited that this enabled her to kind of advance her studies of symmetric components and all the foundational work in terms of power system simulations for grid for fault injection. So the pattern that I'm trying to kind of isolate here is that when our civilization when started building very complex power systems, the complexity starts asking for new ways, new tools, and better numerical approaches to understanding, analyzing, and simulating the system. Eventually, over 100 years, give or take, we actually got to the system that we have today, with well-defined transmission network, all the large generators distributed there, and relatively kind of like one-way passive distribution system, mostly loads. So in terms of civilizational benefits, this highly networked centralized control, in a way, centralized control system actually worked pretty well. So if you kind of like look at basically the losses, the system losses in this system, we see a steady decline. That means that we are continuously improving and reducing the losses. At the same time, this highly networked centralized system also worked well, because you can also see that the price dropped over time significantly from these kind of like early days to today. So we got this I would say somewhat optimal system, but what we were not planning was the need for basically what I like to call D3, decarbonized, decentralized, and digitalized. So this kind of new approach to the grid, which is highly driven by power electronics, and what I like to call software-defined grid, is fundamentally different, because it requires integration, all the renewables at the distribution level, large number of renewables. It also requires us to basically leverage all the flexibility that we might get from all the loads. And we also have another knob, which is power electronics converters, which now enable us to actually drive the integration in the ways that that we can control. Now, similarly, complexity now, of course, in this process of turning power grid into true cyber physical system, where before we had like mostly physical with a little bit of control and communication. Now we are starting to flip the the weight, and most of the weight is actually going on the cyber part, control, communication, and power electronics. We start seeing that software, control software, is becoming a dominant force, which is actually defining what can be done and what needs to be done. Just to put this a little bit in perspective, I like to show basically some of the typical cyber physical or software systems, and kind of like measure or compare basically the software size for specifics in terms of million lines of code. So at the top here we have kind of like a modern high-end car where we have on the order of 100 million lines of code already deployed, and I'm not talking about autonomous driving. This is going to be another layer on top. Just to put this a little bit in perspective, Boeing 787, kind of like another example of cyber physical system, on the order of 1/10 of this size. And if you look at kind of like at the bottom here, Space Shuttle at the time had around like 40,000 lines of code, the complete system. Now the question is, is this, where do we fit? Where do our power electronics devices fit in this whole story? And today's PV inverter, high end with all the grid support functionality and communications is on the order of 200,000 lines of code. So one would argue that this is not a lot, especially kind of compared to some of the even cars. This is really almost peanuts. Well, now the complexity that we are trying to tame here will be interfacing, interconnecting, and deploying not thousands, not tens of thousands, but hundreds of thousands and millions of these cyber physical devices in a specific fashion. Now, when you start looking at this complex system, kind of like here, we have 100 ECUs on the order. We're talking about 100 million lines of code. You can imagine what kind of complexity in terms of software interoperability, communications, evolving the specification, evolving the inverters, and adding, for example, in the case of UNIFI, adding grid forming capability on top, and then evolving it and making it work across these heterogeneous platforms, and making it work also with existing protection on the grid and existing devices. It really starts to be a complex system. And to kind of like demonstrate what kind of problems we can see in these kinds of devices, I'll use this example. In June 2017, there was a really nice report published. There was an outage in SCE territory, Southern California, Edison, where basically all of a sudden they lost 1,200 megawatts of solar power during this blue cut fire. Long story short, what actually happened is that PLL of their solar inverters was poorly designed, and fault that was injected on the line when a tree fell actually made a line-to-line fault, which of course we all know line-to-line faults, they kind of look like, from the voltage standpoint, they look like kind of shifted phase shifted sinusoids, and also the amplitude goes down. The thing was that all the solar inverters were detecting this event as basically low frequency right through event. They started measuring below 57 hertz, where the frequency was constant. It's just because of that fault, it looked different, but the problem was PLLs were poorly designed. And all of a sudden, 1,200 megawatts started disconnecting, and you have a brownout. Of course, it was somewhat localized, but this is a simple example where poorly tested and poorly designed functionality, software functionality of an inverter can actually create a lot of trouble for the overall system. There is another example which you guys probably know even better, is the situation in Hawaii, in their local network, when all the small microinverters were, received updated firmware, and they had kind of like a similar type of event where all of them disconnected at the same point and almost brought down the network. So what we have been doing, and what also Professor Humberto will be talking in the following section, is what can we learn from these guys that, for example, from automotive industry, that design safety critical software that is deployed. First, it's complex, obviously, and it's deployed in millions and millions of cars, and it needs to serve the purpose. So one thing that we can learn, that we have been deploying and advocating for, is really model-based control software development, testing, and lifecycle maintenance. And this is really something that, basically, how do you design your control software for your devices, and how do you do then testing, validation, system integration, subsystem integration, system integration, deployment, and then the lifecycle maintenance. So you're usually starting with model in the loop, and after that you're going to software in the loop, and then in the final phase you're actually doing extensive controller hardware in the loop testing, where your actual controller is connected to a real-time simulation, basically a flight simulator type of situation, where controller is the exact same one that goes into the final product, and you're simulating the physical part of the system. This allows you to extensively test, and this allows you also to have a really good test coverage that hopefully will avoid situations like could have been avoided easily, situation like this. And this is something that automotive industry uses a lot, and we kind of borrowed some of these concepts from them. But one other thing which I think is also relevant for for this group and for UNIFI project in general, is that the process does not end once the control software for, let's say, this grid forming inverter is finished, because then after that we're going into system integration, we're going into interoperability on the network, and so on. And one of the concepts that we have been kind of propagating and proposing is, what happens if we use these digital twins, these models that actually comprise real controllers with real software, together with the model of the inverter and the network, package them neatly. What you have here are actually two EPC power battery energy storage inverter controllers in parallel. And underlying in real-time simulation, you have the network model that actually models both of the inverters. So now these two packaged together, you have a digital twin, which becomes like super useful to basically take it to that next level. Once this, let's say, grid forming inverter with this new functionality developed starts to be integrated on the network with other relays, other DERs, inverters, filters, PV, and kind of high-level controls. So this kind of concept of a useful digital twin that survives beyond just the design and development of the control stage into the life cycle is something that we think is actually very useful, and hopefully will help us accelerate development and deployment of some of the developed control strategies and controllers during this project. And to kind of demonstrate this example, we did a few years back, we did this microgrid model, Banshee microgrid model, with our colleagues from Lincoln Labs at MIT, and demonstrated this concept that these Hill compatible digital twin devices are actually super useful for system integration, interoperability, testing, and also the pre-commissioning for some of these, in this case, smaller systems. So that's kind of our basically our idea, how to bring the usefulness of model-based development tools beyond just the design and into the system integration and lifecycle maintenance. And with that, I'll stop here and hand the talking stick back to Humberto.
My mic, okay. I think you guys can hear me. Thank you. Initially to Eva for the invitation, and Duncan, Callaway as well. I will share my screen over here. Please tell me if you are seeing the screen of the presentation. Should be right now.
Yeah, that's great.
Okay, thank you everyone. So my name is Humberto Pinheiro. I'm at Federal University of Santa Maria. And then I will talk about this course that we have developed together with the Typhoon Hill, and it's available. And it's actually, we have two courses. The first one is for grid-tied converter that basically cover the features of grid-forming inverters, current loop, synchronization, and outer loops as well, DC bus control. And then we have the second module that is addresses the these grid-forming converters. So as Eva mentioned, so I prepared something, but I'm gonna do a little bit different because probably you are familiarized with the content of what I am talking about over here. So what was planning to say here is that we are witnessing a transformation in the electrical power system. We see these renewable energy resources being installed all over, from utility scale to small residential PV systems, from tens of megawatts to kilowatts, to a few kilowatts in residential case. And then we see also the electrification of the transportation. So what does it have to do with the microgrids? The issue is these ones. We have these cars that have lithium battery that can store a lot of energy. So even though that is not in the present, probably in the future, this can also be used to exchange service with the utility, some auxiliary service being exchanged. If you're in vacation, if your car is over there parked, why not use the energy to provide frequency support, for instance? So what I'm trying to say here is this: as we speak, there is the ingredients required to build a microgrid that can operate isolated from the bulk power system is being built. So we have solar panels. My case here, even in Brazil, in developed country, I have solar panels, 5 kilowatts peak. I'm not planning to have a microgrid here, but if the ingredients are here, if you have a battery energy storage system, you have the PV generation, why not? So what is missing? Okay, I need an additional microgrid central controller, probably a circuit breaker, some communication network. The communication network is there. You can use the internet, 5G is coming. So I think the ingredients to have new business models are already there. So the investment to implement microgrid will not be that big. So you have to invest in software, you have to upgrade some firmware, but of course there is challenges. One of those challenges is to make it operate in a stable way in different scenarios. So if you have a microgrid according with IEEE standard 2030, so it's a kind of an entity we can operate connected to the grid, disconnected from the grid, and then we have the microgrid central controller that dispatch the DRs and also control the controllable loads. And now the idea is it's coming. The microgrid is becoming a reality. So yeah, something I have to mention also, it's a kind of this one driving force behind of this implementation also, the renewables and microgrids, is reduction of CO2 emission and global warming. There is an environmental concern, growing environmental concern, that microgrids can help to increase the resilience of the overall system, especially when you have these extreme weathers and extreme conditions. So, you probably want to be in a grid that is more reliable than what we have. If you do have energy storage system, you do have something to control this grid, why not? You understand? So making this introduction, I would like to move to this slide over here that talk about this hierarchical control. Of course, there's different ways to implement a microgrid, but here I consider the classical way. When you come from the tertiary, secondary, primary, have the inner loops of the converters, and then you have these protection devices in different time scales. So you have nanoseconds, microseconds from the device protection inside of a voltage surge converter, for instance. That is, you don't have control on that one. This is just to protect the device to blow up in the event of overcurrent. You have the inner current loops and voltage loops that helps to damp the resonance of the passive filters that are used to attenuate the harmonics of the inverter, also compensate for the non-linearities that might be present in the inverter, doing to the dead time, doing the voltage drops of DC bus fluctuation. So if you want to compensate for that one, you have to design inner loops, have to protect the devices against overcurrent also. So inner current loops helps in this sense. Inner voltage loops for primary control also helps for the compensation of these non-linearities. And then in a different time scale, in a slower time scale here in the range of I would say milliseconds, hundreds of milliseconds, and even seconds, you have the focus of this coarse material that we will show over here. That is the primary control. So the primary control is one way to generate the reference for the voltage loop, and also the reference for generate the reference with the frequency and amplitude of the voltage, so that you can put different DRs in parallel, and they will share power, and then we'll keep the voltage and frequency at the reasonable values in the island mode, and make it possible to dispatch it when it's connected to the grid. So of course, this is done just with local variables. So what's end up having is you have errors, steady state errors that can be compensated, for instance, in the hierarchical architecture by the secondary control. So the secondary control changes the set points of the active and reactive power and voltage and frequency, so that it is kept within acceptable value of the frequency and the voltage. And then you move to tertiary control. That also is not topic of our conversation over here, that, this is economic dispatch, and then try to make the microgrid to operate in terms of environmental or even economic, to give some return to the owner of the microgrid. Well, let's move on. In terms of connection of converters with the microgrid, we have two main forms. That's grid following and grid forming. So conceptually, the grid following, it operates basically as a PQ bar, bus, I would say, PQ bus, in the sense that you have an inner current loop, you have the PWM inner current loop. The reference for the inner current loop can be generated, for instance, using the PQ theory, instantaneous power theory. And then from the command of power and active power and reactive power, you can get the currents that will make the converter or DR exchange this active power and reactive power with the grid. The key ingredient in this case is the synchronization algorithm. So there is a dozen type of synchronization algorithm, from PLL, common filter, you have SOGI, and so on. So there is quite mature literature regarding synchronization algorithm, that from the voltage factor, if you are in the three-phase system, or from the voltage, in the case of single-phase system, you get the the POC voltage, you get the angular position and the frequency. That is used to synchronize the current and make it possible to exchange the desired active and reactive power. In grid forming converter, you don't have this. Of course, you can have some synchronization to connect the system, but you don't need to have that one in there. So what we have, you have voltage control instead of current control. Here, as again, it's possible to implement with current control, but most popular method will use voltage control. So the idea is to synthesize the voltage at the POC. And since the converter is does not have that large inductance as we do have in synchronous machine, so we have to synthesize this inductance if you want to have the droop characteristics as a conventional synchronous generator. So often you have to introduce some virtual impedance. Can be resistive, can be inductive. So in this case here that we are going to address, we decide to develop everything that we are going to present using virtual inductance, not virtual resistance. Similar result can be done with the virtual resistance. Anyway, so the idea here is that from the active power and reactive power computed from the voltage and current at the POC, you get the frequency, the frequency and the amplitude of the voltage that is used by the voltage loop to synthesize at the POC, these quantities at the POC. So conceptually, they are different. There is some authors that are trying to make some link among them and say, okay, it's possible to make one behave similar to another one. But anyway, I prefer to see as two different approaches. So in the course that it's available in the Hill Academy website, and it is free for anyone to download it. We addresses two droop control, one with integrator in the reactive voltage path, two synchronous generator also, in two virtual oscillator as well. So there is another, of course, there is another way to implement primary control, match control, the coupled Hopf oscillator. And if you look, you are going to find different alternatives. But I would say that the most popular one is the Droop Control, and then the dispatchable virtual oscillator also is very promising in my opinion. Okay, let's move on to Droop Control. Probably almost of you know what's Droop Control. It's connected from the voltage and current, the POC, it computes active and reactive power, and then it links the active power with the frequency through the droop coefficient M, and also links the reactive power to the amplitude of the voltage through the droop coefficient M. So it behaves similar to a synchronous machine. So synchronous machines are known to be able to operate in parallel, and since it has a large stator inductance, so basically you can parallel them, and then they have this droop characteristic that is mimicked here somehow in the droop. The droop have been around for a long period of time. So UPS in the 80s, they use droop control for paralleling UPS. Of course, here the problem is a little bit different because we are dealing with, as Ivan mentioned, with large systems, a system that can grow. So the problem is different because you have, in a UPS environment, you have control of kind of devices, DR, the inverters that are connected in parallel. In a microgrid, it's not this case. So maybe you have already something deployed, you have to connect something else in order to make sure that, and then you want to make sure that everything works. So this is becomes a challenge. So that's where simulation comes, this is Hill hardware in the loop who can help to ensure the deployer that they will not run into problems and burn everything, refrigerators and whatever the customer has, because there was incompatibility between already installed grid form inverter with the new installed grid form converters and so on. Okay, so we will find the material, the small signal model. I'm not going through this one because I'm going to limit the time. So you have small signal models that reveals that there is eigenvalues that are associated with the angular power angle and frequency, and complex eigenvalues, and also as real eigenvalues associated with the amplitude of the voltage. So we perform some simulation, and we show, of course, it comes with the idea of do test-driven design, but I cannot just test it. I have to use some previous knowledgement that, you know, in order to tune the parameters and then make the test. So we are not dropping all the knowledgement that has been built for along the years. So the idea is to use the knowledgement that I have available and then add the test-driven design. I will move on fast now because otherwise I'm gonna run out of the time, probably have 5 minutes. So anyway, we do this, the same approach for the synchronous, virtual synchronous generator, where we derive a model based on elementary machine, three-phase machine. So we have the dynamic equations for this machine. So we have two cases here. One case when you have the feedback of the reactive power in the gap. Another one when you have the feedback of reactive power on the POC of the DR. Okay, so we implement these dynamic equations in a C code, and then the inverter emulates a synchronous machine. So we have the swing equation, we have some damping coefficient that's associated with the droop. So dP and dQ are related with the droop. Here, one difference is that you can somehow decouple the steady state and transient performance. Now in droop, if you change the droop coefficient, you change the transient, you also change the steady state. Here in this implementation of the synchronous machine, also it's possible to have these two characteristics decoupled. The local qualitative behavior depends on the operating points, since the system is nonlinear. And then there is some additional damping that we introduce. So let's move on. So this is, I'm gonna move on. So basically, the third class is virtual oscillator. So here, the main conceptual difference, in my opinion, is the fact that it's not attached with the, you know, the legacy system. There is no link with of oscillator with the generator, a synchronous generator. So the basic idea is to have this property of, if you pick up two oscillator and couple this oscillator, there is a possibility, depending on the parameters of them, that they will oscillate in the same frequency. And the neat concept here is the fact that it provides power sharing among inverters that are controlled using virtual oscillator. This is was something very interesting that you know, have been shown. So here we use inductive droop also. The voltage generated by the converter is coming from the current of the virtual oscillator. Virtual oscillator has this LC tank here that define the frequency and non-linearities that provide there is one part that is you know, provide energy for this LC tank, another one that dissipate energy. So there is a stable equilibrium point of a limit cycle now with a stable equilibrium, not equilibrium point, but the equilibrium set. Now there is this oscillation that will be stable with the desired amplitude. Of course, there is some disadvantages. There is some non-linearities. There appears harmonics. And then, okay, let's move on. Here it's also demonstrated for inductive cases. In the literature has been demonstrated for resistive case. Here for inductive case, we have shown that there is a relation between the reactive power in the voltage and active power in the frequency for this virtual oscillator. In the case of the dispatchable virtual oscillator, is similar, but you know, it operating now for beta coordinates. We have this frequency over here that defines the nominal frequency. We have one term here that is for the compensate for the I would say, power, and then another one for the voltage. So it's not, it's demonstrated over here that it's this equation here that we have shown in the material that you have available over there in the Hill Academy is give a better picture for this dispatchable virtual oscillator in the way that we see it, in the sense that we have here in this part over here, you see that the active power is associated with the frequency, and the reactive power is associated with the voltage. Of course, there is a coupling terms over here. Now you see that the voltage also affect the amplitude of the voltage, also affect the frequency. The frequency not that much, is not clear how the voltage is affected by the frequency. But anyway, this implementation of this differential equation, you have active and reactive power set points, and you have voltage and frequency set points as well. So, and then the Droop coefficient can be related with this alpha and VO in a similar way. Okay, let's move what was mentioned, test-driven design. So the idea is this one. Okay, you have designed your system, you have different alternatives, which one I'm going to implement? So let's run, let's make an automated test, define a case, I would say. When we have two DRs, you have linear and nonlinear loads, as well as a short circuit over here. You have the microgrid central controller that doesn't implement it, just set the set points for the DRs, and you have the grid. So we didn't cover all cases of the microgrid, but we pick up some of them. That is grid connect mode, a transition mode, and planned island that we think that is one tough event, in the sense that it's the grid suddenly disconnected. So we would like to see how this DR will share power, how it will behave in terms of steady state transient during this mode. And also in island mode. In island mode, you might have a linear load, you might have nonlinear load, you might have short circuit. You might want to see how these DRs recover from a short circuit. So this is, we test it. It has been developed automated test to run hundreds or even thousands, if you have the patient, tests in order to and then we see the result in a neat environment, that is the Alluri. So here is how we parameterize the test using the Typhoon Hill IDE. And then here is how the results of the tests are presented. So we are interested in those tests. Here is for island mode. So here, the first one is linear mode, nonlinear mode, and short circuit. You have two cases in the short circuit. The short circuit with 500 milliseconds and a short circuit of 205 milliseconds. So the same test is applied for all controllers that we have described before. So the idea is that we just look for the one that fails. So here is summarize the results for the dispatch steady state test. We see that the two integrator, the Droop with two integrator has, one of the best results. The DVOC is not bad as well. There is a fail here, but if you look to the result, when you see one result that fails, you have to go there to see how significant is that one. Is there a way to change some parameter and make it to pass the test? So this is one important point. So here the frequency has been changing from 57 to 63 to 1 to 1 hertz, and the voltage has been increased from 200 volts to 240, 10 and 10 hertz, and the results are summarized over here. Oh, here is not bad here. The virtual synchronous generator with the feedback of the reactive power at the PLC also did well. So it's how this is the results, each one of those points at one simulation that has been captured, analyzed, and plotted the results. So in summary, our primary controller considered pass the frequency support steady state test. So all of in terms of frequency, there was all have 100%, in the test that we have performed in steady state. The Droop present a significant error on the volt-var curve among all older primary controllers. We have already identified this using the steady state analysis, using small signals. So this was not a surprise. But the test revealed it. You understand? So this the virtual synchronous generator with reactive power on the gap fail in the volt-var curve test, I would say, which has been attributed to the drop in the virtual inductor that we have introduced. So even though that dispatchable virtual oscillator failed in a point of the volt-var curve, its performance was satisfactory. So if you look to the point where it fails, say, okay, this is with a small adjustment, you can make it pass. Okay, so the transition test over here is unplanned island. So here basically we assume that there is a delay between the secondary controller and the primary controller of the different DRs. And then the set point is, the results of the set depends on the set points. So we consider different set points for the active and reactive power. And also we consider that the microgrid has different loads from 0 to 70% of full load. And also in this case, from 0 to 70%. So from this result, we see that DVOC results in a best performance. So I will move on. So basically, the idea is to there is this for power sharing, you know, also how the power was sharing among the two DRs. So this is here is a challenge as well now, because we have this scenario, but the real life might be different. Maybe you have already installed a grid following inverter, you want to introduce a grid forming inverter with a battery energy storage system to build up your microgrid. So the situation is a little bit different, or you might have two of those units, you understand? So anyway, okay, I think my time is over here. Just want to show one result to summarize over here. So here is the short circuit test where the DVOC has failed. We have this 500 millisecond short circuit. The current is limited by the inner current loop. It fails because the voltage, there was an over voltage after the short circuit clearing. What I mean is that this is difficult to predict from linear model. So you have to do this on simulation. So, and then we see that the voltage eventually recovers, but there is a over voltage indicating that you have to somehow update the states of the primary controller when you are in short circuit, assuming that you are able to identify that the voltage has dropped, the current is in the limit. So is it possible to somehow update the state so to avoid this over voltage when returning from the short circuit? So basically, what I like to say that this work has actually is not we derived this controller, but of course in literature it was already being published. There is a lot of information available in the literature. The material that you have seen are available now free of charge in the Hill Academy site. We have all these materials that I have shown is available there. There is the slides, there is this video, and also there is these files that we have used to run these simulations. Oh, in addition, there is these Jupyter files over here. So if you can design the droop coefficient with the eigenvalues and participation factors using these Jupyter script, Python scripts to start up your analysis or your simulation. Okay, I have to. This is not my only work. The Marcio Stefanello, Professor Marcio Stefanello, also work on this one, especially on the Droop Control, dispatchable virtual synchronous oscillators. Professor Fernanda also recorded the audios. If you listen to the audio, Fernanda is there. And Henrique Maiago, he implemented the Python script that were used in the test-driven design in the results that you have shown. Thank you. I'm sorry if I pass a little bit of time. Are you guys still there?